Okay, so whether each of these are even or odd. So this one here is even. How do I know it's even? Well, because all the powers of x are even. All right. What would I know then? I know the graph for even functions is reflexive over the y-axis. So they have like a horizontal line of reflection. And I know the equation, I could check it by saying if I plug in a negative x value everywhere, what do I get back? If I get back the same original function, then that's what makes it even. For example, in this one, if I plugged in negative x to the fourth plus negative x squared plus 2, if I put in negative x for all the x's, now when I do negative x to the fourth, a negative times itself 4 times would just be x to the fourth, and this would turn into x squared. And you can see that I get back the original function, f of x. So that makes it even. Let's look at this one. This one here is odd. So that's because I noticed that all the powers of x are odd. So what does that mean on the graph? It has 180 degrees rotational symmetry about the origin. Okay. So we also kind of say it's reflexive about the origin. That also means you could reflect it horizontally and vertically. That's the same thing as 180 degree rotational symmetry. So we would notice that on the graph of odd functions. In the equation, what happens is if I plug in negative x for x everywhere, I'll get the same function but the opposite. Like, so all the numbers and stuff will be the same, but all the signs would be opposite. I would get negative f of x. So for example, if I plug in negative x to the third and negative x in for x, then when I simplify that, a negative times a negative will be a negative x cubed, a negative 1 times x cubed, you can think of it, minus x. Then to really show that it's the opposite of the original function, we can factor out that negative 1. And you can see that that's negative the original. All right, so that's what makes it odd. Absolute value of x. This one is interesting because you can't go by the powers, right? Because that's a power of 1, but it's actually an even function. So we just have to go by the graph in this case. Okay, so the graph, and by the way, picking out the odds and the evens, that just works for polynomials. That's not the definition or anything, it just helps you pick it out. This thing by the graph, right, if we look at that graph, it makes this V, which has got that symmetry over the y-axis, right? And if I plug in negative x for x, that ends up being just x, right, or absolute value of x. Those are the same thing. So you can see that when I plug in a negative x, I get back to the original. And that's really the definition. F of negative x is equal to f of x. That's the definition there of an even function. Cosine doesn't have any powers, so like it doesn't have any exponents and stuff. So now we have to think about the graph. And this is why we're talking about even and odd functions today. It's important to know cosine is an even function. So the graph of cosine looks like this, which is reflexive about the y-axis. All right. The definition would be if I plug in negative x for x, I should get this function back. Let's see if that's true. Well, if you look at the graph, it is. Like, let's say x is right here, and I move the same distance in the other direction and plug in negative x, I get the same y value on the graph. We can start doing some examples, but examples aren't enough. They only work if you have a counterexample. But let's just take a look for a second on the unit circle. Let's say I do cosine of negative pi over 3. Is that going to be equal to cosine of pi over 3? Are those equal? Well, cosine of pi over 3 is this value right here, because here's pi over 3. Right? And then negative pi over 3 is this angle here. And you can see that the cosine value, let's change color here. cosine value is this leg right here, not the dotted line, but the solid red line. So they both have the same cosine value. All right, and if you think about how this works, of course that makes sense. If I made like 2 pi over 3, I would be over here in quadrant number 2, and negative 2 pi over 3 would be that same angle over here in quadrant 3. That would be negative 2 pi over 3. And then those would have the same cosine value right here. So it is even. All right, so here's some examples of what we would be dealing with. It's kind of what I just went through with you here. So if you take the sine of pi over 6, I get 1/2. And then if I do the sine of negative pi over 6, I get negative 1/2. So that means that this function is odd, because sine of negative x equals negative sine of x. It's the same value, but just the opposite. Now again, this is not a proof, just proving one example that it works for pi over 6 and negative pi over 6. Right? I could look at the graph of sine over x. I didn't draw it that great, but if you flip that 180, let's see if I could do that here. Actually, I've never tried to rotate in this. If I flip it, let's try that again. You get the same graph, right? So it's got that symmetry. If we look at moving over to an angle of x, we'll get this y value here. So if that's x, we'll get that y value there. We'll call it f of x. If I go to negative x, the same amount of space, the y value that we would get right here would be the same distance from the origin as f of x, but it would be in the negative direction. So you can see that it is an odd function. Sine is odd. Cosine is even because of what we just talked about. Cosine of negative x equals cosine of x. So that makes it even. And then tangent, well, let's check it out. What happens with tangent? If we plug in negative x for tangent, what do we get back? Do we get back tan of x? Do we get back negative tan of x? Which one is it? Maybe it's neither, and tangent is neither even or odd. So tangent of pi over 4, that's going to be 1, right? Because pi over 4 is here at the 45. Right? So sine and cosine are equal to each other. One way to think about it. These two sides are equal. So that's got to, so they have to be 1 when you divide them. So my y over my x is 1 over 1, which is 1. Tangent of negative pi over 4 is down here, and that's going to be negative 1. So it looks like tangent is odd. In fact, we should probably look at the graph of tangent. I don't think we've looked at it yet this year. So at 0, tangent is 0. At pi over 2, tangent's actually undefined. So it's at pi over 2. At negative pi over 2, tangent is also undefined. But what's happening in between there? Well, as the angle grows from 0 to pi over 2, tangent grows and goes to infinity. It gets larger and larger and larger, unbounded. And the same thing would happen in the negative direction here. So that's what the graph of tangent looks like. And then there's more sections. The same section would just repeat itself on the next interval. Whoops, I should do it like this. Right? And the next interval. And these are every pi over 2, these asymptotes, right? So if I took and rotated this guy that has symmetry about the origin, right? It's the same graph if I flip it. So this one is odd. In class, we're going to take a look, we're going to work on graphing tangent because that was just a quick little rudimentary graph of tangent. You really should be looking, we should graph tangent for ourselves. Okay, so then, is secant an even or an odd function? The question becomes, is the secant of negative theta equal to secant of theta? Or maybe, whoops, or maybe it's equal to negative secant theta, right? So this one is going to be even. Why do I know that? Because secant is really 1 over cosine. I forgot to put the negative in there. And then we know that those would be equal, meaning this would be equal, so it's even. It's because it's related to, it's another way to write cosine, essentially, the reciprocal of cosine. So if cosine's even, then secant's even. For the same reason, cosecant is odd, because it's the reciprocal of sine, and then cotangent is also odd because it's the reciprocal of an odd function. All right, so here's some examples that we could do. If cosine of x equals negative 1/4, what is secant of negative x? So the first thing is, if I take this cosine of x equals negative 1/4, I'll say secant of x equals negative 4. You can just flip both sides, right? And then it's saying, what is secant of negative x? Well, I know since secant is even, right? Let me get my pointer out here. I think I have a pointer. Yeah. Since I know that secant up here is even, I know that secant of because they want to know what's secant of negative x. So secant of negative x, since secant is even, is equal to secant of x. And secant of x we just showed is equal to negative 4. So you can say secant of negative x is equal to negative 4. Basically, because the function's even, you can kind of ignore the negative inside here. It's equal to secant of x. Okay. Let's look at cosecant. If cosecant is equal to 4, what is sine of negative x? Well, if cosecant is equal to 4, then that means 1 over sine of x is equal to 4. And then I would flip both of those. So I'd get sine of x equals 1/4. And then I know sine is an odd function, right? So sine of negative x, these people are really loud out there. Sine of negative x equals negative 1/4, okay, because sine is odd, so I guess I could write it this way. Sine of negative x is equal to negative sine of x. And we know from down here that sine of x is equal to 1/4. So then that means this is equal to negative sine of x, which is negative 1/4. All right, if tangent was equal to negative 1/5, what is cotangent of negative x? Well, cotangent of x would be negative 5, because we just take the reciprocal. And then we know that cotangent of negative x is equal to negative cotangent of x. And then so we know cotangent of x from above is equal to negative 5. So cotangent of x is negative 5, right? So then we know it's negative 5, so it's equal to 5. Okay, the reason we knew this, just to remember, I didn't say it, I don't think. The reason we know this right here is because cotangent is an odd function. So that's what gets us to figure out what cotangent of negative x is. It's negative regular cotangent. We know regular cotangent is negative 5, so it just switches the sign and becomes 5. All right, so I'm going to have you try these on your own. Maybe not. I'll do this one with you. All right, so if we're looking for cotangent of negative x, cotangent of negative x, that's equal to, well, tangent's odd, right? So that's going to be equal to negative cotangent of x. So now it's just going to be equal to negative cotangent of x. And we know cotangent of x will be sine of x over cosine of x. The over 2's cancel out. We have negative 1 over root 3, which equals negative root 3 over 3. All right, because cotangent is an odd function. Let's see, on the second one here, what is tan of negative x? Well, I know that tangent is an odd function, so tan of negative x is equal to negative tan of x. And I can make tan of x based on my sine and my cosine up here. So tangent of x, it's going to be negative, and then tan of x is sine over cosine, so negative root 3 over 2 over negative 1/2. So this is going to turn out to be a positive value because the negative and the negative. And then the 2's cancel, and you get root 3. Okay, over here we have what is sine of negative x. We know sine is an odd function. So sine of negative x is equal to sine, oops, it's odd, so we want negative sine of x. All right, and then can we figure out what sine of x is based on if we know cosine and tangent? I think we can. If tangent is -1 and cosine is negative root 2 over 2, that means sine has to be positive root 2 over 2. How do I know that? Because tangent is equal to sine over cosine. And since cosine, oh, sorry, they tell me up here, tangent is -1. So then I know -1 equals, and they tell me cosine is negative root 2 over 2. So it would be sine of x over negative root 2 over 2. And if I wanted to solve for sine over x, I can multiply both sides by negative root 2 over 2. Or I could just kind of know that that's what it's going to be. Okay, but if I multiply both sides, these cancel, and I get, whoops, I get on the left side, I didn't mean to make that mark there. On the left side, I got -1 times negative root 2 over 2 is just positive root 2 over 2. So I knew that right here. So we're still trying to figure out what sine of negative x is. I just wanted to show you how I knew sine of x is root 2 over 2. I plug that in here, and I get negative root 2 over 2. Okay, let's see what we have here. We have some co-function identities here. So if we think about in a triangle, I'm going to call this angle here alpha, and this angle here beta. And I'm going to name the sides opposite them as capital letters. So I'll call the side across from the 90-degree angle C. I'll call the side across from the angle beta a capital B. And I'll call this side across from alpha a capital A. Let's write our trig ratios. Sine of alpha is going to be A over C, because opposite of alpha is A and C is the hypotenuse. Sine, so let's do cosine of A, or alpha, sorry. So now I'm going to do this guy here, cosine of alpha. So cosine is adjacent B over hypotenuse C. Now let's do sine of B, or sine of beta. So beta is here, sine is opposite, which is B, over hypotenuse, which is C. And then cosine of beta is adjacent, so that's going to be A over hypotenuse, which is C. Okay, what do you notice about these? We notice that sine of alpha is equal to cosine of beta. Why do you think that is? Well, it's because they're in the same triangle, and also these are co-functions. Remember when I drew these unit circles here, when I said that's theta, then we made another triangle, and we said if we draw this triangle up top here, this angle here is the complement of theta. So then instead of calling this sine, we called it cosine, because it was the sine segment in this triangle. It was opposite the angle, right? So it's sine, but it's the sine of the complement. So it's because these angles are complementary that those two things are really the same thing. So what we know now is that if I say that sine of alpha is equal to, cosine of beta, I could say sine of alpha is equal to cosine of 90 minus alpha. All right? And instead of 90, let's use radians. All right, and there's some cool stuff happening here on the graph too. If you think of like the graph of sine and how this transforms it and makes the cosine graph. Again, we could maybe investigate that a little further in class. But these are going to be called the co-function identities. So basically, the sine of one angle is equal to the cosine of the complementary angle. All right, and really there's a nice kind of description here in these drawings of these circles, of these unit circles and triangles. Maybe I'll just give you a quick refresher on that. How much time has gone? No, this video is getting long. Let's just know that sine of alpha is equal to cosine of pi minus 2 minus alpha. And then that works the other way around, like 2. I can say cosine of alpha is equal to sine of its complement. All right, so it works either way with sine and cosine. Does it work with secant as well? You betcha. Let's use a theta here. I'm just changing the angle up. Because it's the cofunction. That's why they're named that way. So any function and its cofunction, you could say they're equal to the complements. Okay, this will come in handy in some situations. It's tested on the SAT, the sine and cosine version anyway. I've seen it show up. That's why they're called cofunctions, right? Because secant and cosecant, you know, are equal if you make the complements. Oh, a nice breakfast from NHS. I'm not going to do the explanation with these geometric circles.
Thank you.
So here are some examples of how you could use it. So if tan of theta is 1.28, find cotangent of theta minus pi over 2. Well, this isn't quite the complement, right? I want to write this as pi over 2 minus theta. Then I can say the two things are equal. So I'm going to say that cotangent of theta minus pi over 2 is going to be equal to cotangent of, I'm going to factor out a negative, pi over 2 minus theta. Okay? So now this is the complement. And I know that cotangent is odd. So think about this as our angle. Cotangent of negative x would be equal to, since it's odd, negative negative cotangent of regular that angle, so pi over 2 minus theta. That's because of our even and odd function thing, right? Now, because of our cofunction thing, since cotangent is the cofunction of tangent, I could just say that's equal to negative tangent of theta. Okay, and I know that tangent of theta is 1.28, so I get negative 1.28. So again, these are just some identities that we know, and we'll do some practice in class to help this make a little more sense. Okay, lastly here, I have one more page, but I might save this for you guys. Yeah, I think I'm going to save this for class for you guys. We'll see. Get rid of those guys. All right, if sine of x equals negative 0.37, find cosine of x minus 2. So again, I want this to be pi over 2 minus x. So first, I'm going to write cosine of x minus pi over 2. I'm going to factor out the negative. Nice language in the hallway. So I can factor out the negative, and now it's the complement. Since cosine is an even function, cosine of, if I view this as my x, this one giant x, cosine of a negative angle is equal to just the regular cosine of that angle without the negative, right? So that's nice. I could do that. Now by my my cofunctions, so this guy was because it was even. I could kind of drop that negative or whatever. I could say cosine of negative angle is equal to cosine of that, of the positive angle. Now because it's a cofunction, the cofunction or the complementary function of cosine is sine, and I could just say it's equal to sine of x. And I know that sine of x is equal to negative 0.37, so we have negative 0.37. That's what cosine of x minus pi over 2 is equal to. Ratios. Yeah, maybe I'll talk about this real quick. So ratio review. How can you write the following trig functions in another way? I could say tan of theta is equal to sine of theta over cosine of theta. We know that. We're just going to rewrite all of these in terms of sine and cosine. This one is equal to 1 over sine. And don't forget to write your thetas. This one is equal to 1 over cosine. And this one is equal to cosine over sine. Okay, so we're going to see how that will help us solve some equations. So some examples here are using our ratios. So it says solve for x on 0 to 2 pi. So I think one of the goals you can do is change everything to sine and cosine. So tangent is sine of x over cosine of x. And you have to write the of x every time. Plus sine of x times secant is 1 over cosine of x. And that whole thing is over cosecant of x, which is 1 over sine of x, times tangent, which is sine of x over cosine of x. I know this is mind-numbing. We have to try to get through this. Well, it'll make more sense, like I said, when we start doing examples. I definitely don't want to do this during class. You'll fall asleep. On a video, at least you could watch it, pause it, come back later, finish it later. You can take little breaks. All right, so we want to start simplifying this left side now anywhere that we can. So I notice, first of all, on the bottom, these signs will cancel. Up top, I'm going to multiply these and make them into like one fraction. So I have sine of x over cosine of x plus sine of x over cosine of x. Then on the bottom, I've got 1 over cosine of x equals 1. All right, so then up top, let's see what happens on the top here. Well, now I can add these together. They have the same denominator, right? I'm just double checking, make sure I didn't miss anything. Okay, so I could add those together. Another thing you could do is you could call them both tangent, but I'm going to leave everything as sine and cosine for now. So if I add the tops, I have 2 sine of x over cosine of x equals 1. Oh, and it's over 1 over cosine of x. Now I can simplify this complex fraction by saying 2 sine of x over cosine of x times the reciprocal cosine of x over 1. I take and I flip that guy. Let's see here. Now here the cosines cancel, and I get 2 sine of x equals 1. Now I can divide both sides by 2. Sine of x equals 1/2. And then I know what angles have a sine value of 1/2. Those would be positive 1/2, the little short guys. So that would be pi over 6 and 5 pi over 6. What's our interval here? On 0 to 2 pi. So those are our solutions. Whew, that was intense. All right, let's try this guy. Let's use our ratios to turn everything into sine and cosine. So I have 1 over sine of x times cosine of x plus cotangent, which is cosine of x over sine of x, over secant, which is 1 over cosine of x, times cotangent, which is cosine of x over sine of x, equals negative root 2. So we want to solve this equation. Okay. It looks like the numerator, the same thing happens. Cosine over sine plus cosine over sine. I'll add those together and get 2 cosine of x over sine of x. That's what the numerator shakes out to be. Here the cosines cancel. It's 1 over sine of x. It looks like the same equation pretty much. Same method. Now instead of dividing by 1 over sine of x, I'm going to multiply by the reciprocal of sine of x over 1. These cancel, and I get 2 cosine of x equals negative root 2. I divide by 2 on both sides, and I get cosine equals negative root 2 over 2. Where's cosine negative? And it's the medium guy, so it's over here. So we have this angle and this angle, and that's the medium guy, so it's the 45s. So that's going to be x equals 3 pi over 4 and 5 pi over 4. I think it's probably the same restrictions. Yeah, it's the same directions. All right? And then we have our Pythagorean identities. I'm going to ask you to look these up to finish your homework. What are the Pythagorean identities? Maybe like how many are there? As well, make sure you have them all. And we'll discuss these in class because this video is getting very long.